Okay, brand new chapter on electrochemistry. This chapter we're going to be starting off with redox reactions review, since you should have learned redox reactions. I think that was in 1A. But we're going to review it because it's been a while, and we're going to be using some of the redox ideas in electrochemistry. Electrochemistry covers things related to, as you might expect, electricity and chemistry. And lightning is a great example of electricity. It's a very dramatic display of electricity and electrical charge. A key point in electrochemistry, electrons flow away from negative charge. They're negatively charged themselves, and so if you have a negative charge, the electrons are going to not want to be around that negative charge. They're going to flow towards the positive charge. So electrons go from a negative area to a positive area. Just magnetism related stuff. The way that lightning works is in a thundercloud, there's lots of air that's moving around, and that can cause water droplets to collide with ice particles. Electrons get exchanged. It's basically a lot of small events of friction, like static electricity buildup, and it creates positive charges and negative charges, and those separate out. You get positive charges that accumulate on the ice crystals, and those get floated up to the top of the ice cloud on the rising air currents, and those negative charges are going to remain in the white or the wet slushy bottom that's not as icy of the cloud. When that charge separation starts to develop, it builds and builds and builds until it eventually reaches a point where it has the potential to just flow through the air, the water, the things that are around it. Most lightning occurs within one thundercloud or between two thunderclouds, so it's all happening up in the sky rather than actually touching down. But if the cloud gets close enough to the ground, then that negative charge on the bottom of the cloud can induce a positive charge on the ground, and then it can cause the lightning to connect to the ground or to a building or whatever. Batteries are a big component of electrochemistry. Batteries are typically composed of at least two substances that have different affinities for electrons. So we can think of like electronegativity, the unequal sharing of electrons in a bond. It's a sort of similar idea here, but we're going to be talking about ions and stuff. So when we separate these two substances, one will develop a positive charge and the other a negative charge, and those will exist until we can connect them, like with a wire or something, that will let electrons flow from that negative end to the positive end. And this is all kind of within the realm of redox reactions, or it's related to redox reactions. So we need to remember how to do redox reactions. This will play an important role in electrochemistry. So we've got two mnemonics. One's listed here, oil rig. Oxidation is losing electrons. Oxidation is losing, that's the oil part. And then the rig part, reduction, is gain or gaining, also electrons. So that's our oil rig mnemonic. So if you're losing electrons, that's oxidation. If it's gaining electrons, that's reduction. The other popular one that I know is Leo goes Gur. And the reason that Leo goes Gur is because Leo is a lion. Leo the lion goes Gur. This stands for losing electrons oxidation, gaining electrons, reduction. So it's the same idea, basically the same words. It's just that Leo goes Ger has electrons explicitly in it. Another way that we can think of oxidation and reduction is by oxidation state numbers. So oxidation is an increase in oxidation state. And reduction is reducing or decreasing the oxidation state. There's also another kind of older definition of oxidation is gaining oxygen, which isn't always true, and reduction is reducing the number of bonds that you have with oxygen, which is probably also not always true. But that can sometimes be a way to identify oxidation and reduction. Some important things that we have to do in redox reactions: not only do we have to balance the mass in terms of what elements do we have present, but we also have to balance the charge, and that's what makes it more difficult than balancing regular reactions. So our key for redox reactions, remember, we want to split our equation into two half reactions. We want a reduction half reaction and an oxidation half reaction. We'll balance those individually for charge and mass, and then combine them back together to get our whole redox reaction. Okay, so oxidation states, we've got a bunch of rules that you maybe haven't thought of in a while. I don't know why you would have. They're fun, but I don't know why you would have thought of them. There's lots of other fun things to think about. So, turn on Do Not Disturb real quick. The rules in order of priority. Free elements have an oxidation state of 0. And for things like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, horses need oats for clear brown eyes, these normally exist as diatomic gases. And so Cl2, H2, O2, N2, for example, those are all going to have an oxidation state of 0. Any free element, oxidation state is 0. So that's our top priority. We also have monatomic ions will have an oxidation state equal to their charge. Easy enough. So for example, sodium in sodium chloride is going to have a +1 charge. The chloride is going to have a -1 charge. If we had Fe3+, that's going to have a +3 oxidation number. Straightforward. In a compound, the sum of the oxidation states is 0. In a neutral molecule, it's also 0. And in a polyatomic ion, it equals the charge of the ion. The overall oxidation states have to add up to the charge of whatever the chemical is. I think that's a better overall summary. For compounds, it's 0. For neutral molecules, it's 0. For polyatomic ions, it has to add up to whatever the total charge is. So equal to charge on the compound / chemical. That's really, in a way, it's not different from Rule 2. We're just expanding it to multi-ion or multi-atom groups. In their compounds, in their ionic compounds, metals have positive oxidation states. Group 1 metals always have an oxidation state of +1. They're also always going to have a charge of +1. So that's convenient. Our group 2 metals always have an oxidation state of +2. They're also always going to have a charge of +2. Anytime that I'm writing number and then plus or minus, that's charge. Anytime we're writing plus or minus and then a number, That's oxidation state. Number second for oxidation state. And then we've got a set of more rules kind of built in. For nonmetals, they have oxidation states according to this table. Entries that are higher on the list take precedence, take priority. So for example, fluorine always gets a -1 in any compound with another nonmetals. Hydrogen's next, then oxygen, and then it's working our way from right to left on our periodic table, group 7A, group 6A, group 5A. And then if we have anything else left, it just gets assigned whatever the balance is. So entries lower on the list will take a charge to balance. So one example of this happening is hydrogen peroxide is H2O2. H2O2 is a neutral molecule, so its overall oxidation state is 0. Hydrogen is higher on the list than oxygen, so hydrogen gets assigned a +1. We need to balance that out. We've got 2 hydrogens, 2 oxygens, and so this means that oxygen has to take, surprisingly, a -1 instead of the -2 that it normally takes. So that's one instance of this rule coming into play where we take priority. So since hydrogen's higher on the list, it gets its pick. Oxygen is next and all that we have left, and so it has to fill the balance. So for our half reaction method, we can do it in acidic solution or in basic solution. They're very similar. There's just one extra step that you do if you're in basic solution. So if we're in acidic solution, that means that we have excess H plus relative to the hydroxide, or relative to the hydroxide. So we can have H plus in solution. We can have it floating around, no problem. Our first step is that we have to assign oxidation states to all of our atoms, both on the reactant side and on the product side. That will let us identify the substances that are being oxidized. Those will have an increase in oxidation number, and things that are being reduced, which will have a decrease in their oxidation number. Usually we've got one thing that's got one atom, one element, that's got its oxidation state increasing, and another one that's got its oxidation state decreasing. So we can separate them out. You don't have to identify them as oxidation reduction necessarily, just one's going up, one's going down, and we'll separate those out. So we separate into 2 half reactions. One of them's for our oxidation, one's for our reduction, and then we balance those with respect to mass. So with respect to our elements, this is the balancing that we've done in every other circumstance. So we're going to balance everything other than hydrogen and oxygen, and the reason that we're doing everything but hydrogen and oxygen is we're in an aqueous solution. And since we're in an aqueous solution, we've got effectively unlimited water, and we've got also effectively, since it's acidic, unlimited H+. So balance everything that's not H and O. And then we can balance oxygen by adding H2O. And we can balance hydrogen after that, balancing H+. this order is a little bit more effective since when we're adjusting our H2O, we're also adjusting our H. And when we're adjusting our hydrogen with H+, we're just adjusting our hydrogen. So it lets us kind of do that freely. And then we have to balance the half reactions with respect to charge by adding electrons. We're adding electrons which have negative charge. So this is a very easy place to make a mistake about where we're trying to add the charge. So check what's our total charge on our reactant side, what's our total charge on our product side, and then we can move one of them down to match the other one. We can't increase charge because we're adding negative charge, so it's going to decrease the charge. So higher charge side gets the electrons. And we're going to do that for both of our half reactions. And then since we don't really ever have electrons just floating around in solution, we're going to make the electrons balanced out. So for each of our half reactions, we're going to multiply them by 2, 3, 4, 5, whatever we need to get the electrons to balance out. So they have to be equal on both sides to cancel. So if we've got 6 electrons on the reactant side, 6 electrons on the product side, one of those will be our reduction, one will be our oxidation. Then when we combine those together, since we had 6 and 6, we can cancel those out. We'll see examples of doing that. If your electrons don't cancel out, you've done something wrong. And then we can add our half reactions together and cancel out electrons and other species, usually H plus H2O, stuff like that. And then at the very end, go through and do another check. It's very easy to make mistakes combining half reactions, especially if they're not easy ones. It's very important to double check. For regular balancing of reactions, I don't think it's that important. Usually people get it right. For balancing redox reactions, I would say I get it wrong about 25% of the time, 20% of the time. I'm guessing that you probably will also get it wrong 20 to 25% of the time, unless you're very fastidious about checking everything along the way. All right, let's balance this redox reaction. This is about as simple as it gets. And we've got the rules along the side to help us out a little bit. So we want to assign oxidation states. Our oxidation states for a free element is going to be 0, so we can assign copper and aluminum, not the ions, charges of 0. For monatomic ions, where it's just one atom and it's an ion, it's the same as the charge. So we get +2 for copper 2 ion and +3 for the aluminum ion. Then we can identify the oxidation and the reduction numbers, or the half reactions. So aluminum is going from a 0 to a +3. That's increasing its oxidation state. It's also losing electrons. It's going from 0 charge to positive charge, which is the same as losing negative charge, gaining charge. So our oxidation half reaction is the aluminum going to Al3+, aluminum ion. And our reduction half reaction is copper 2 plus going to copper. We're reducing the oxidation state number. It's going from a +2 to 0. And then in a lot of other problems, we would balance these with respect to mass. We've got 1 copper on each side, 1 aluminum on each side, so we're already balanced. We don't have any oxygens, we don't have any hydrogens, so we can skip to making the number of electrons, balancing the half reactions with respect to charge. So our charge for our oxidation reaction is 0 on the left. It's 3 plus on the right. For our reduction half reaction with copper, it's 2 plus on the left, and it's 0 on the right. We can add electrons to reduce the charge. Since we've got a +3 on our aluminum ion side, we can add 3 negative charges to cancel out that 3 plus and make it 0 charge. We can do the same idea for our reduction half reaction. We've got a 2 plus charge on our copper. We can add 2 electrons to make that charge also 0. So now we're balanced with respect to charge, and we can make the number of electrons equal. So for our oxidation half reaction, we've got 3 electrons. For reduction, we've got 2 electrons. We can bump those each up to 6, because that's their least common multiple, I think is what the term is. It's been a long time. I think it's least common multiple. So we're going to multiply those to get up to 6. So we'll multiply the left one by 2 and the right one by 3. So we'll have 6 electrons for our oxidation. We've got 6 electrons on the product side. On our reduction, we've got 6 electrons on the reactant side, so they're on opposite sides. They're the same number. That means that we can go ahead and add them together. So combining those, get 2Al plus 3Cu, 2 plus goes to 2Al 3 plus 3Cu. And I'm going to write the electrons in just to show that they're there. Since we have 6 on the product, 6 on the reactant, we can cancel those out. And then we can verify that our charges balance out, or that everything is balanced. So we've got 2 aluminums, 2 aluminums, 3 coppers, 3 coppers. Our total charge, 3 times 2 plus, 2 times 3 plus. So it's balanced. Questions about that one? All right. I'll let you try this one. Balance the redox reaction in acidic solution. So we've got H plus reacting with Cr to turn into H2 and Cr2 plus. All right, so that was a small amount of time. This is a slightly more difficult one. We're just adding a little layer of complexity. So we need to first assign our oxidation states. We're going to start with things that are in their naturally occurring form, elements. So that's going to be our H2 and our Cr. Those get values of 0. Chromium normally exists as metal. Hydrogen normally exists as H2 gas. And then we move on to monatomic ions. Hydrogen has a 1 positive charge, so it gets a value of +1. Chromium gets a +2 since it has a 2+ charge. And we can split these into their half reactions. So we're going to be splitting these into H+ goes to H2. This is our reduction half reaction because hydrogen is going from a +1 state to a 0 state. It's reducing its oxidation number. That makes our other one our oxidation half reaction, which is chromium going to chromium 2+ ion, or chromium 2 ion. Now we can balance these with respect to mass. Our chromium one, as you can hopefully see, 1 chromium, it's balanced. Our hydrogen one is not balanced. We've got 1 hydrogen versus 2 hydrogens. So we can add a coefficient of 2 in front of our H+ to get it balanced out. Scooch this over. So we're all balanced with respect to mass. Our normal balancing, now we do charge balancing. So take a look at our charges. Grand larceny, grand theft auto, burglary. Sorry, wrong charges. Our charges are 2+ and 0 for our hydrogen half reaction. And there's 0 and 2+ for our chromium half reaction. So we're going to add electrons. Electrons have negative charge, so we can bring one of them down to match the other side. So we can add 2 electrons to the H+ side of our reduction half reaction. That will cancel out the 2+ and bring us back down to no charge. And then for our chromium half reaction, we can add 2 electrons to the product side to bring our 2+ down to a 0 charge. So now they're both balanced with respect to charge, and conveniently, our number of electrons is the same. We've got 2 on the product side for our oxidation reaction, 2 on the reactant side for our reduction half reaction. So we can combine the half reactions together and we'll get 2 electrons plus 2H plus Cr goes to H2 plus Cr2 plus 2 electrons, and we can cross out the 2 electrons part. You could also just choose to omit them. For more complicated ones where we have H2O and other things that we're going to be canceling out, it's helpful sometimes to write it out without crossing anything out, just so we copy it down, and then go through and cross everything out and rewrite it for our final answer. And then finally, we can go through and check and make sure everything's balanced. So for charge, we've got a 2+ on the product side. We've got 2 times a 1+ for 2+ on the reactant side. We've got 2 hydrogens and 2 hydrogens, 1 chromium and 1 chromium. So we're all balanced up even Stevens. Stepping up the complexity a little bit more and getting rid of our rules on the side. How are we feeling about redox reactions? Would you like time to try this? We will also be doing stuff in basic solutions, so I can also just run through it real quick. Give you time to work on a basic solution one. Okay, no strong feelings either way. I'll go ahead and just do this one. All right, we want to balance our redox reaction. We need to first assign oxidation state numbers. And everything has a charge, so we're not assigning zeros to anything here. Our iron, our Fe2+, put this in correct color. It's going to be a +2. We're going to have an overall -1 for our MnO4 permanganate. We're going to have a +3 for our iron 3+, and we're going to have a +2 for our manganese 2 ion. Within this MnO4- ion, we've got oxygen and we've got manganese. Manganese is not a group 1 or a group 2 metal. It is also not fluorine, hydrogen, oxygen, group 7A, group 6A, group 5A for our nonmetals, right? So that's, since it's a transition metal, it's going to pick up the balance of everything else. So oxygen gets its preferred pick of -2. And we've got 4 of them. So overall, that's -8 oxidation from the oxygen. We need to get to an overall of -7. So -8 plus what number gives us -1? It's +7. And so manganese in this compound has a +7 oxidation number. And then we can separate those out into our half reactions. Our oxidation half reaction is going to be our iron. It's going from a +2 to a +3. Increasing oxidation number is increasing the oxidation state. So oxidation, we've got Fe2+ going to Fe3+. And then on the other side, our reduction, we've got permanganate, MnO4- going to manganese 2. Let's just go ahead and balance the iron one so that we're done with it already. You can hopefully see that we've just got 1 iron on each side, and so we just have to balance charge. We've got 2+ and 3+. We can add electrons. We can't remove electrons, so we can reduce our charge. So we can add 1 electron to the product side to bring the 3+ down to a 2+, and now it's all good to go. It's mass balanced, it's charge balanced. Our reduction half reaction is not so simple. So in our reduction half reaction, we now have to actually balance something other than just whatever metal we've been doing. So our manganese is good, right? We've got 1 on both sides. Our oxygens, however, we've got 4 on the reactant side. We currently have 0 on the product side. So to balance that out, we're in an aqueous solution. It's acidic. We can add as many H2Os as we want to either side to make things balance out. So let's add 4 H2Os, since that will add 4 oxygens. So now our oxygens are balanced, but we've made another problem for ourselves. We've got 8 hydrogens. So we have to balance hydrogens, even though we didn't have hydrogens to begin with. We've got 8 hydrogens on the product side. And we can balance that out by adding 8 H+, 8 protons, 8 hydronium ions on the reactant side. So now we're balanced with respect to mass. All of our atoms are even number on the left and the right side, and we get to balance charge. For our charge, the product side is a little easier here. We've got a 2+ overall charge. On our reactant side, we've got a 1- and 8 1+. So 8+ plus 1-, we've got 7+. To get these to balance out, to get 7+ down to 2+, what we need to do is add 5 electrons. And that will bring our charge down 5 to make it a 2+. So now our charges are balanced and our masses are balanced for both of our half reactions. The next step is that we need to make sure that our number of electrons balance out. Our reduction half reaction has 5 electrons in it. Our oxidation half reaction only has 1. So we multiply our oxidation, our iron reaction, by 5 to get the electrons to balance out. So 5 Fe2 plus goes to 5 Fe3 plus 5 E minus. And then we can combine our half reactions. And I'm going to not keep all the same colors. I'm just going to write them all the same color. So 5Fe2 plus 5E minus plus 8H plus permanganate. So that's everything on our reactant sides. And then everything on our product sides. It also doesn't matter the order that you write these in. So 5Fe3 plus 5E minus plus Mn2 plus 4 H2O. And now we can look at both sides and see if we've got things to cancel out. And we do. We've got 5 electrons on both sides. You should always end up with electrons to cancel for these problems. But if we look at everything else, we've got iron 2 plus and permanganate on the left side. We also have H plus. We don't have any of those repeating on the right side. Sometimes, for more complicated ones, you'll end up with H2Os to cancel out as well, possibly even H pluses or hydroxides. Questions about any of those steps? I don't really want to balance another one in acidic solution, so we're going to skip that and move on to basic solution. Yeah. That's because I forgot to post the slides. They're up. You just can't see them. Sorry. I'll fix that.
No, it's okay. I just wanted to make sure I wasn't like tripping or anything. But
It's probably I just didn't post the module that has them in it. Yeah. All right, so for balancing in basic solution, as we well know, there's excess hydroxide floating around in solution. If we balance it according to our basic or our acidic principles like we've been doing, and we showed that there's H plus in solution, we know that there's really not that much H plus floating around. There's lots of hydroxide floating around. That H plus would get used up pretty quick. But since we have excess hydroxide, we can have excess hydroxide floating around. We're going to add a single step, just one step, that makes this different from balancing it in acidic solution. So we do our normal balancing in acidic solution steps, including the balancing with the H plus to get our hydrogens balanced. And then we neutralize all of those H pluses by adding hydroxides. So if we have 7 H pluses on our reactant side, we add 7 hydroxides to both the reactant and the product side. On the reactant side, those H pluses and the OH minuses turn into waters. On the product side, they'll just be hydroxides. So H plus turns into H2O, and then we'll have leftover hydroxide on the other side. There's another way that you can do it that I personally don't know how to do because I've been told by many people this way is just better. It's easier. I think the other way of doing it is like playing this weird balancing game with H2O and OH minus. Because like H2O has one extra hydrogen compared to hydroxide, and so you can balance your hydrogens that way. This way, you're just adding one extra step onto the method that we already know. It's nothing new. It's not like a whole new thing. Okay, so let's balance this redox reaction in basic solution. Our first step is what? Writing the oxidation numbers. So for I2, iodine normally exists as I2, so that's going to have a value of 0. That's our only free element. Next up, we have monatomic ions. We've got iodide. Iodide has a 1 minus charge, so it's going to have a -1 oxidation state. We have permanganate again. So oxygen is going to get its preferred -2, and manganese gets its +7, like we talked about on the previous example that we did. And then in MnO2, we've got a neutral molecule this time. Oxygen still gets its preferred -2, and then to balance out those two -2s, we give manganese a +4. And then we can split these into our half reactions. In a lot of cases, you don't actually have to assign oxidation state numbers first, but it's helpful if you want to label what the redox labels are, reduction or oxidation. Okay, so our iodine is going from -1 to 0, so that's actually increasing, so that's our oxidation half reaction. I minus going to I2. And then our reduction half reaction is permanganate going to manganese 4 oxide. And we can balance these. So for our oxidation half reaction, we'll balance our iodines. We've got 2 on the product, 1 on the reactant, add a coefficient of 2 to balance it out. And then we need to balance charge. Currently, we've got a 2 negative charge and a 0 charge, so we can bring that 0 down to a -2 by adding 2 electrons. And then we can balance our reduction half reaction with our manganese. So our manganese is already balanced out. That's very convenient. We've got 1 and 1. I don't know why I'm doing that in that color, but so 1 and 1. Our oxygen, as you can see, is not balanced. We've got 4 and 2. So to get those balanced out, we can add 2 H2Os. That adds 2 oxygens, so we're up to a count of 4. And now we've got hydrogens to balance out. We've got 4 hydrogens on the product side. To get those balanced, we can add 4 H pluses on the reactant side, and now we're balanced out with respect to mass, so we can move on to charge. Somebody say, no, wait, we're in acidic, or we're in basic solution. We can't do that. I'm going to pretend that I heard it. No, wait, we can't do that. We're in basic solution. So we have to do our extra step. Right, we have to add hydroxides to balance out our H pluses. We have 4 protons on the reactant side, so we need to add 4 hydroxides. We have to do the same thing to the other side. So that we don't mess up our mass balance. And then our 4 H pluses and OH minuses turn into 4 waters on the reactant side. If you want to at this point, you could cancel out some of your waters. Let's just leave it for later. And then we can balance out charge. So on our reactant side, we've got a neutral water, and we've got 1 permanganate, so we have a 1 minus charge. On our product side, we've got a 4 negative because of our 4 hydroxides that we added. We can only make charge decrease, so we can bring our 1 minus down to a 4 minus by adding 3 electrons. So now we're balanced with charge and with mass, and we've got hydroxides instead of hydroniums. And then we get to multiply them so that they get the same number of electrons. And this is one of the places where redox reactions can get a little bit sloppy, where we can run into trouble, because we have to multiply the left, our oxidation half reaction by 3 and our reduction half reaction by 2 to get them up to 6. So there's a lot of coefficients that are going to be changing. This is one of the prime places to make mistakes. So multiplying the left one by 3 and the right one by 2, we'll have 6I minus goes to 3I2 plus 6 electrons. And I'm going to squeeze a little bit more space out of this. And then on the right side, we've got 6 electrons plus 8 waters plus 2 permanganates goes to 2 manganese 4 oxides plus 4 waters plus 8 hydroxides. And then we can add those together. So 6I minus plus 6 electrons, 8 waters, 2 permanganates goes to 3 iodines plus 6 electrons plus 2 manganese 4 oxides plus 4 H2O plus 8 hydroxides. And then we can cancel things out if they show up on both sides. The one that we're always going to do, of course, are electrons. So 6 electrons, 6 electrons. Cancel those out. We did it. And we also have extra waters. So we've got 4 waters on the product side, 8 waters on the reactant side. Goodbye 4 waters, and hello 8 minus 4 for 4 waters. And then this is the step where you would go through and check, make sure that everything's actually balanced out. But I'm going to skip that. And then there's another one in the slides for you to practice, and that's where I'll stop for today, unless there's any questions about redox stuff. All right, and then we'll learn about the electrochem stuff starting next week.